effectively bends as the forces arising both within the engine and from the suspension are applied to it.
Rover used computer analysis to assess the performance of the new design. Here, a vertical slice shows the results of a simulation of the loads and stresses which a running engine would have to bear. Yellow areas are very lowly stressed, while the red indicates some areas which are tensile, but acceptably so. A different simulation helped Rover to minimize noise. This is an exaggerated representation of the vibration of the engine. The different colors here indicate the amount of displacement in the system. Computer analysis prompted some modifications to the design, but there were still many details to be worked out.
One of the major areas where the long bolt had an effect was in the design of the cylinder head gasket. Because we had gone for the most flexible bolt that we could possibly achieve, the clamping loads that we had were rather lower than is the case in conventional engines. That meant that the cylinder head joint had less load on it than would normally be the case. Our original design scheme showed very simple rings sealing the combustion forces and the liquid sealing for the oil and water passing through the cylinder head joint being achieved by a liquid gasket which required no load at all and which would solidify anaerobically once the cylinder head was bolted down. That scheme ran into some problems which forced us into using a different concept. What we decided to use was a new type of cylinder head gasket which had only recently become available, which sealed all the liquid using elastomeric beads printed onto the gasket. And these beads required a very much lower load than is the case for normal gaskets. This allowed us to take the load which the bolts gave us and concentrate the vast majority of it on the cylinder sealing rings, which is where we needed it.
The first engines were launched in 1989 and 1990. But why could Rover make a long bolt engine when no one had succeeded before?
It has indeed been the engine designer purist's dream, if you like, for many years. The thing which has made it possible for K Series are developments in the materials front. The bolt itself is made out of a boron steel with a very, very closely controlled yield strength. Without that closely controlled yield strength, we would not be able to maintain the load applied by the bolts within the close limits that we need. And without those close limits, the flexibility, the loads applied on the engine would be non-uniform, inconsistent, and would cause us problems throughout the structure.
The forces which the bolts apply to the engine sandwich have to be precise. The engine could certainly be made, but careful design thought also had to be given to keeping the compression force consistent in mass manufacture. To achieve this, Rover uses a technique called the snug torque and turn tightening process. Bolts are dropped into their locations to be tightened to a relatively low torque. This is called the snug torque. They are then given a further full turn.
By applying the snug torque, we've got all the components in contact, the bolt head in contact with the seating face on the cylinder head, and from then on we know that we're stretching the bolt. So we stretch it by one thread pitch by giving one turn. That's where we come to a rather unusual area of this bolt's performance, in that tightening will have taken the bolt near to yield. It's more usual for cylinder head bolts to tighten them straight into yield. But with this very long bolt and the aluminium engine, what we have done is taken it near to yield, and then the first time the engine warms up, the different expansion of the aluminium and the bolt stretches the bolt by very nearly another millimetre, and that's what takes it into yield.
The clever design makes sure that the clamping load is consistent. Perhaps surprisingly, the bolts themselves are not made by Rover, but by a specialist manufacturer in Germany. Rover do, however, detail the bolt's specifications very tightly.
The conical taper is designed to ease assembly to guide the male thread into its mating component. In the case of the other end, the head end, the radius underhead is absolutely critical. It's the main stress raiser for this area of the bolt. If that's not right, there is a risk of bolt failure. If the head is off square, as manufacturing says to some degree it must be, then a bending load is placed across that change of section. Therefore, we must have a suitable distributor of stress around that corner to ensure that we don't get failures.
The success of the K Series engine can be put down to new materials technology which made the long bolt possible. But success was also the product of a willingness to rethink accepted engine design. But after all that design effort, why does Rover not make the bolts itself?
Rover don't make bolts themselves in general because it's not cost effective for us to do so. Rover particularly don't make difficult bolts, and that is a difficult bolt.